Cool cats and kittens, Mr. Harmer's back, and today we are going to talk about intermolecular forces of attraction. These are forces of attraction between molecules, not within the molecules. So we're not talking about covalent or ionic bonds now. We're talking about forces of attraction between molecules. It's how well those molecules can stick to each other, not how well the atoms within a molecule stick to each other. It's how well molecules stick to each other. Now, I've created a nice video for you. It's a demonstration video entitled Intermolecular Forces, Surface Tension, and Vapor Pressure. If you want a better understanding of what I'm talking about right now, you need to watch that video because it'll help explain things, I think, by seeing it much better than me sort of giving you a lecture. So remember, there's a video demonstration related to intermolecular forces for you guys to watch as well. Now, there are several different types of intermolecular forces. We're going to start with something called dipole-to-dipole interaction. Now, these occur between molecules that are polar. For instance, if you were to draw the Lewis structure for sulfur dioxide, you would have something like this. You would have a non-bonding pair of electrons, or a lone pair of electrons, above the oxygen pushing, or above the sulfur pushing those oxygens down into a bent configuration. That makes it asymmetrical. And of course, these electrons here are not being shared equally, and so because it's asymmetrical, you're going to end up with a positive end and a negative end of the molecule. We call those polar molecules. PCl3 is another example. These electron pairs are not being shared equally, so the chlorines here end up having extra electrons, and the phosphorus is electron deficient because those shared electrons from phosphorus seem to be spending more time around chlorine than they do phosphorus, because chlorine is more electronegative than phosphorus. So it has a positive end and it has a negative end, which makes it a polar molecule. Now, as you can imagine, if I have a positive end to a molecule and a negative end of a molecule, and I have more than one of them, and I chuck them into a box and shake it up, aren't those positives and negatives going to stick to each other like tiny little magnets? Yeah, they probably will. And that interaction, that dipole to dipole, the positive to negative interaction that we're talking about here, is called a dipole to dipole interaction. Let me give you two very, very simplistic examples. The first is between H and Cl and hydrogen chlorine. These are two separate hydrogen chlorine molecules. Hydrogen's electronegativity is lower than the electronegativity for the chlorine. Chlorine has a higher electronegativity, kiddos, than hydrogen. That means the pair of electrons being shared between hydrogen and chlorine spends most of its time around chlorine as opposed to spending most of its time around hydrogen. As a result, the chlorines end up having more electrons than they have protons in this molecule, because that shared pair is spending more time around the chlorine atom, here and here. Well, as a result, isn't it spending less time around the hydrogen atom? And wouldn't that give hydrogen with fewer electrons a positive charge for part of the time? And the chlorine would have a negative charge for part of the time. So if you threw these into a box, wouldn't the positive end of one hydrogen chloride be attracted to the negative end of another hydrogen chloride, and they would start clumping or sticking together? This is called a dipole-to-dipole interaction. It occurs between molecules that are polar. Here's another example. Fluorine is more electronegative than bromine. So in this molecule, bromine fluoride, this pair of electrons will be spending more time around the fluorine atom than it will the bromine atom. That would mean this part of the molecule would have a positive charge, while this end of the molecule would have a negative charge. If we had two bromine fluorides, wouldn't the same be happening with the other? Wouldn't this shared pair be spending more time around the fluorine and less time around the bromine, giving the bromine a positive charge for part of the time and the fluorine a negative charge? That means these two molecules would stick together. We call this a dipole-to-dipole interaction, and it is a form of intermolecular intermolecular attraction. It's not within the molecule. It's not intra. It's inter, which means it's between the molecules. And this type of intermolecular attraction that we're talking about is called a dipole-to-dipole interaction, and it occurs between polar molecules. Let me contrast that with a nonpolar molecule. Let's take hydrogen gas. The Lewis structure for hydrogen gas, H2, is that. It's very simple. This pair of electrons is being shared equally. In fact, it can't be shared more equally. Those two hydrogens obviously have the same electronegativity. So if they're being shared equally, there isn't a positive end and there isn't a negative end. Therefore, this molecule is nonpolar. And there are no dipole to dipole interactions because there's no positive or negative end to the H2 molecule. So this does not have a dipole to dipole interaction. All right, let me give you another example of an intermolecular force of attraction. Let's talk about hydrogen bonding. You may have heard this before in your biology classes. Hydrogen bonding is discussed quite a bit there. It turns out it's a special case of dipole to dipole interaction. And for this to happen, within the molecule, a hydrogen atom must be bonded to either nitrogen, oxygen, or fluorine. Those are the three most electronegative elements: nitrogen, oxygen, and fluorine. So if you can imagine for a moment the hydrogen fluoride molecule. There is the Lewis structure for hydrogen fluoride, and you can see that they share a pair of electrons right here. Now, the electronegativity of fluorine is so high that that shared pair spends almost all of its time around the fluorine. Doesn't that make this fluorine have a negative charge because it has an extra electron, the one that it's supposedly sharing with hydrogen? And doesn't it give the hydrogen end a very positive charge because its electron that it's supposed to be sharing with fluorine is spending all of its time around fluorine? Now think about the hydrogen atom at the nuclear level. Doesn't it consist of a nucleus with one electron around it? Well, if this electron is spending all of its time around fluorine, what's covering the nucleus now of the hydrogen atom? You're right, nothing. It becomes what we like to call a bare proton. It's a strong positive charge, it's a proton, and there's no electron covering it any longer because that electron that was covering it is spending all of its time around the fluorine atom. So we have a bare proton, which means another electronegative element from another molecule could get really, really close to it. So take for example water and methanol. Water has hydrogen bonded to oxygen. The electron that's being shared between hydrogen and oxygen is spending all of its time around oxygen, and that makes the hydrogen a very positive charge, and there's no electron covering its proton at all. In methanol, don't we have the same situation? Don't we also have hydrogen bonded to oxygen, so that pair of electrons is spending all of its time around oxygen, giving it a very negative charge, and this hydrogen has a bare proton. Now, can't this oxygen that's so electronegative get really, really close to that bare proton and form a very, very strong intermolecular attraction? And it does. It's much stronger than a normal dipole-to-dipole interaction because there's no electrons covering the hydrogen's nucleus now. So that oxygen can get very close to it and form a stronger intermolecular force of attraction. Here, let's look at hydrogen bonding in water. This is a water molecule right here, and this is a water molecule right here. This bond and this bond within the water molecule are called intramolecular. They're within the molecule. And we learned earlier that those are called covalent bonds. However, the interaction between different water molecules is an intermolecular bond. And since it occurs between a hydrogen and either oxygen, nitrogen, or fluorine in a separate molecule, we call it a hydrogen bond. We usually call them just H bonds for short. So the green dots, kiddos, represent hydrogen bonds between water molecules. These are all intermolecular bonds. It means that they're between water molecules. Intra means it's within a molecule. So the intramolecular bonds are here and here, the red lines between the hydrogens and the oxygens. These are all intramolecular bonds. That's not what we're talking about today. We're talking about these intermolecular forces of attraction between water molecules. And so long as hydrogen is bonded to either nitrogen, oxygen, or fluorine, the three most electronegative elements of all, we can have that bare proton that exists. And another nitrogen or oxygen and fluorine from a separate molecule can get really close to that bare proton and form a strong intermolecular force. Okay, I think that's good enough for now. Hopefully when you watch the demonstration video, it'll clear a bit of this up. Plus, we're going to talk about it more in the next video, and we're going to give lots of examples. So stay tuned. It was nice being with you today, kiddos.